Okay, last but not least, the important topic of spectrum for 5G. Because as we're here over in Geneva, Switzerland, WRC 15 is underway with lots of delegations from around the world making some global decisions on what spectrum might potentially be harmonized. So we're going to have a discussion about that, focusing on the Americas region. And leading our discussion and moderating a panel is Monica Paolini of Sensafili Consulting. And Monica has a rich history in the industry. It says in your bio you're an expert. Is it true?
I'm not sure about that.
Okay. Well, we have other experts with her today, so we hope that you will listen to them, but also have in mind some questions that you might be able to ask of the panelists.
Vicky, thanks you so much for the introduction, and welcome to the panel on spectrum utilization. And I'm delighted here to have two panelists, Hank Kafka, VP of Access Architecture and Analytics at AT&T, and Eduardo Esteves, VP of Product Management at Qualcomm. So here are the rules of the game. I will ask them to introduce themselves, and then we're going to have a little bit of a discussion, because spectrum is really crucial. The new spectrum and how spectrum is used is crucial for 5G, as you know. But at any point in time, if you have any question, raise your hand, and somebody with a microphone will come and give you the microphone, say who you are, and ask the question. It's important that we have it as, your participation is important, so feel free to ask as many questions as you want. But before we get started, I would like you to introduce yourself, what you do, and what is that you're working on 5G right now. Hank, do you want to get started?
Sure, thanks. So I have responsibility for access architecture across wireless and wireline at AT&T. So 5G is a key aspect of the architecture areas we're working on the wireless side, clearly. And the wireline side kind of feeds into that nicely, because you have to do something with all that data once you get it off the air and move it somewhere. And especially as we move into HetNet and small cell capabilities, the wireline and the wireless have a lot more interdependencies in terms of how we put them together. I also have the team that represents AT&T in standards organizations, and including the folks down at WRC. And I've got a team that also looks at analytics, which also kind of becomes important, especially as you're going into HetNet. It's not just how much traffic, but it's exactly where it is and when it's there, and how do you kind of pull together the network-based analytics and tie those into the overall network architecture and directions.
Eduardo?
Yes. So I'm with the Qualcomm Research and Development team, and I lead the product management function for the research organization. And in the context of 5G, my team is responsible for basically coordinating the activities that we're doing in R&D and reaching out to potential partners outside the company to really do kind of early trials, collaboration, R&D collaboration, and also some discussing standard strategy. So we will work very closely with operators and other vendors in the industry.
Yeah, okay, so, there is a lot of debate of, what is 5G, what it's not, but I think that for spectrum, we actually know, not exactly the detail, but we know exactly where the trend or where we're trying to go. And basically, it is to expand the range of frequencies that is being used for cellular. But if we think about, move a few years back, when we started thinking about 2.5, initially mobile operators and vendors were like, oh, 2.5, it's just too high of a frequency. We cannot do it with cellular. That's dangerous. Then 3.5 came along, and it was like, no, we don't know about that. 5 gigahertz, forget it. But now, we use Wi-Fi. LTE Unlicensed is using 5 gigahertz. So we're getting more and more comfortable with higher frequencies. And maybe you can provide us a little bit of an overview in terms of we're moving both to lower frequencies and higher frequencies. And so what does it change? Why is it that before it was impossible and it's possible now, and desirable, as a matter of fact? So maybe we can start with the lower frequencies. What is the use case? What is the opportunity there? What should we expect?
So lower frequencies are important for broad coverage, and they provide a key capability with that. So, expanding to lower frequencies gives you more opportunity to kind of put those functions in place. The 600 megahertz auction in the US is, one of the upcoming direction that adds to that. And then, 5G can be used in existing bands as we go on as well. And I agree with you. It is kind of interesting that how we define low frequencies in the context of 5G is quite a bit different than the way we defined it in the context of 2G, 3G, and 4G as we've gone forward. But there's a lot of technology gain that is helping with that. I think, though, that another kind of important part is that as you look at the highest frequencies capabilities, it's got short range, it's a HetNet kind of environment, and you can have it great coverage in this room and turn your head and lose it, or walk out the door and lose it, depending on the situation, how you set up. There are ways to compensate for some of that, but that could lead to a very unreliable experience. So in a lot of the cases, especially when you're going for the highest frequencies, you end up using lower frequencies, I should say sub 6 gigahertz frequencies to be more specific. They can provide, we call an anchor frequency in some cases, but kind of a base frequency or a primary frequency that can carry the signaling, monitor what's going on, keep the connection active, and even help opportunistically switch between and steer among the higher frequencies depending on what's going on. So the combination, as you go up in the very high frequencies and or low power frequencies and other kinds of things, the combination of the existing frequencies at high power and those capabilities with the very high frequencies that give you great capacity but are less consistent is a powerful combination that makes the two work together better than either one alone.
Yeah, I'll just add to, I think I completely agree with Hank. Coverage, combination, lower frequencies are needed for coverage, also in terms of efficiency for some of the applications you're talking about, 5G, in terms of massive type of IoT type of application. We're going to really need the lower frequency bands for that. And the anchor aspect that Hank mentioned is also very important. I would also highlight the fact that, I think the Moore's law is helping us too, because in the past, we handle, perhaps a handful of different frequency bands, and now we're capable of handling several tens and frequency bands in the same device, and that is helping with the view that you can continue to integrate more and more capabilities into the devices and support more and more different frequency bands without having to incur a huge cost. So that is also helping with that view that we can now go to higher frequency bands, and the fact that we're going to continue to talk about multiple bands. Just like in LTE, we have 40-something different bands. I don't foresee that 5G will consolidate the number of bands. So if anything, we'll just keep expanding it.
Yeah, and one of the key features of 5G that we're going to see more and more bands not only to be used but to coexist and work closer with each other. So it's not traditionally you might have 2G, 3G, 4G networks, but they largely exist independently. And so 5G is a framework to bring all of them together. And I think that the concept of an anchor channel, it's an entirely new concept that it's emerging right now. And maybe you can explain how is that work, because this is a very powerful concept, I think, in terms of helping us manage the overall traffic.
Yeah, and as with a lot of concepts, it's something that's not brand new, but it is new. and it's being used in a much more powerful way in 5G. But if you kind of think of even 4G LTE and carrier aggregation, right?
Yeah.
Carrier aggregation says, this is my primary channel, and then you identify a secondary channel, and you kind of carry the signaling over the primary channel, and then you have the secondary channel that gets added to it for bandwidth. And you can even kind of, in some of the dual connectivity, you can expand that and do some other things. But that kind of concept that goes along with the earliest phases of carrier aggregation, where you have a primary and a secondary, that's kind of the primary turns into the anchor channel, if you will. And then you can have a lot of different secondary channels and work with them in a very dynamic manner. So I think that the extensions in 5G are going to allow more dynamic and more variety in the secondary channel, and also allowing the, in some of the proposals, the primary channel can actually communicate information about the secondary channels and tie it in that direction.
So that you basically can increase the efficiency of the spectrum. Even given the same amount of spectrum, you can use it more efficiently because you can juggle traffic more
right.
efficiently.
You've always got a known connection that allows you to maintain the reliability, and it gives you the opportunity to exchange information to help optimize exactly how you're using which frequencies.
Yeah. Eduardo, I have a question for you, which I hear oftentimes, and there is kind of like adding new bands. It's a good thing from the infrastructure point of view, but from the handset, it's a little bit of a nightmare. So how many channels can you use before you get something that is really heavy, really the battery life is an issue? How do you deal with that, all of that?
So as I mentioned, in fact, we've been increasing the number of bands supported in phones, and that trend will continue. Now we have already designs that support, 20 different bands simultaneously, could support 20 different bands simultaneously. Sometimes the OEMs decide not to populate all the passive components that are needed around the RFIC. But I just think that trend will continue. When we go to very high frequency bands, one of the challenges there is going to be power consumption, because millimeter wave front-end receivers, the RFIC part is going to be kind of is one of the challenges. And so that will have to be taken into consideration in terms of how many bands we're actually going to support, at least initially. But over time, I don't think that will be an issue.
Yeah, I guess that the high bands they don't have to be on all the time if you don't, because you have the anchor type of
The anchor is a requirement. As Hank mentioned, reliability is going to be a big issue. Not in a bad way. It's just that the way the propagation is, the way that it turns out blockage. Handsets can get really blocked just depending on how you handle it. You can completely eliminate a band. So you need to rely on that anchor to provide the continuity of the service and the user experience. So that's going to definitely be a must.
Yeah. Okay, let's move on to the higher bands, because that's a lot of excitement there, because when you think about the amount of spectrum that is available there, the ability to use it for mobile handsets, it feels like, that's like amazing, So maybe you can provide first sort of a general overview of what's going on above the 6 gigahertz, and then we can dig down. And again, if there is any question from the audience, feel free to raise your hand, and I will try to remember to pay attention to you. So,
okay, let's start. So there's a lot going on. In fact, a lot going on this month and for the next week and a half now with the work going on in WRC. So the FCC had the NPRM that kind of talked about the 24 to about 70 gigahertz range, and identified some specific bands in that region. There's also, activities looking at the 6 to 24 range and kind of in that dimension. And so, one part of it is which bands you can find, what are they or aren't they used for now, what can coexist, what can share, what can shift around, and what degree of harmonization can you get as you look across the different countries, because a lot of different countries do a lot of different things in these bands from a historical perspective. They've got a lot of different uses. And then the kind of piece that goes on top of that is, okay, what do we do with the standards? Because if you kind of think about the standards and the technology, this is a nanosecond or about a gigahertz. If everybody talks about a gigahertz, that's a gigahertz, right? It's about how, that's the wavelength of a gigahertz is about a foot. It's about how far light travels in a nanosecond. So if you think about what we've done before, 600 megahertz, about there. 2.5 gigahertz, about in there, right? 60 gigahertz kind of range, about like that. It's very different. And so to say, how do I, can I get one standard, one waveform, and what's the right place to split the waveform, and when to use what, when, and how, and why? That's one of the really interesting things that's got to get worked out in standards as well as we kind of expand the frequency range. So, there are some activities that are looking at saying we should be able to use the same 5G waveform, maybe with some different parameters and numerology behind it, but use the same waveform for sub-6 gigahertz all the way up through maybe 30 gigahertz. Others kind of think, nah, you can kind of stretch from 6 to 12, okay, but then you should do something different above 12. So there's a lot of different discussion points about the best methods and approaches, because you do get some very different behaviors, both in the physics of the waves, the structure and physics of the antennas, and then even what you're doing in terms of the power and radio amplifiers and the can't even say silicon technology anymore, right? The IC technology that you need to drive the bands.
Yeah, and I guess you want to have as few interfaces as possible for simplicity, but you don't want to pay a price in terms of spectrum efficiency.
Yeah, and you don't want to suboptimize.
And so that's how difficult it is to get to the optimal.
So we actually believe that is a way of designing a system with some basic fundamental principles that can be unified. And when we look at low frequency bands and high frequency bands, we can basically scale a lot of the aspects of their interface that would allow us to maintain certain simplicity on the design, as well as enable the features that are needed to fully exploit the benefits of going to high frequency bands. So this is the kind of things that are being debated now, beginning. We'll see more of that debate once the study item starts into GPP early next year. But we're confident that we can actually achieve something that is very unified across different bands.
How do you feel that within the industry, oftentimes there is the operators that push for something, the vendors and different vendors that might push for different things. How controversial do you think that this is going to be? Is it just a question of try to understand what's the best, or it's a question of different players having different agendas that are difficult to be?
This is not new, right? So the concept that different players have different interests and perspectives has been at the heart of the industry for all these years. What I've seen, though, is since the discussion around 5G started, couple years, maybe 2 years or so ago, I actually have seen a convergence of the ideas a lot faster than we had seen in the past. So I'm actually very positive about it. I think once the activity starts in 3GPP, really the standardization activity, what we'll see is really a focus on the merits of the technical proposals, and in the end, what's going to come out is really the best proposals.
Yeah, the sort of the feeling that you get is because nobody has really worked so far out that they are so so strongly tied to a solution. There might be everybody might be more open-minded in terms of discussing different options instead of defending what they already built. Maybe that's. Now, let me ask you, in terms of whenever you sort of hope for a new spectrum allocation at the national level, you also want to make sure that that allocation doesn't only exist for, say, in the US or in the UK or any other country. What does it look in terms of finding bands that can be used globally so that you can have some, the whole ecosystem can develop for the whole world, or many countries, not just the US?
It's challenging. I mean, that's summary. There's a lot of existing use. Some of the existing uses are different in the different bands. There's kind of a convergence around some, but that's kind of the first phase of that is what's going on right now in WRC 15. Right? So WRC 15 is looking at saying, how do we create the study items and work items for the next 4 years so that in WRC 19 we can kind of bring things together and get ourselves as consistent as reasonable across the globe, or at least regionally, depending on how everything gets set up and where it aims. So it's a pretty critical piece of work that's going on right now in WRC 15, and that's the beginning of the work. And then, the next 4 years will be the key to convergence.
Right. Sorry, go ahead.
No, I was going to just add, although I think the goal of achieving this common spectrum bands is ideal, and the WRC work is going to help. From a device semiconductor player, we are kind of assuming that that's not going to happen. We're going to have to design for multiple bands, and that's the reality of it.
Yeah.
And just kind of the progress that's been made by the device guys and the chipset guys that make that possible has just been they're kind of my heroes in terms of how they've grown in support of the bands. I have to say that, right? When we started out with LTE, it was hard to get 3 or 4 bands on a single device and chipset, and we're saying it's kind of that's not the constraint by any means that it had been in the early days, and capabilities of getting there. It's just been tremendous progress over the past 5 years that has been made. So it's been very encouraging.
Yeah.
You have a question?
Oh, we have a question. Sorry. Okay. Question over there, Mike. As I promised, I forgot to.
So with LTE, we had some unanticipated dichotomies created after the fact, in most cases, that forced the industry into 2 camps. So take an example, FDD, TDD, and where we had to form a GTI, and the whole Chinese side and the 2.5 gigahertz range became the TDD camp and the FDD camp on the other side. I know for AT&T, there's really no issue because we're all FDD. But what are the unanticipated dichotomies that might occur as we start finding new spectrum to use, that we could anticipate them now and try and address the challenge that having 2 different opposite things, approaches, might let's say, you'd be able to overcome them in advance. Let me give you a couple of, one example is FDD, TDD. I don't even know if above 6 gigahertz there is a distinction. I assume there is, but I don't know whether one is FDD or TDD. Is there?
So let me kind of try. I actually disagree with your first statement that we had an unexpected dichotomy in LTE between FDD and TDD. From before the LTE standards were completed, there was a recognition that LTE needed to support FDD and TDD. And one of the key things in the basic frame structure of LTE, by very intentional design, is to set up exactly the same frame structure that can apply across FDD and TDD. You have some variations clearly in turning it around in a gap, but it was designed to be one single frame structure that worked with FDD and TDD. And the FDD parts in general were implemented and standardized first because that's where the first spectrum it was going into was set up for, but TDD was close behind, and you know, it's been very successful. That's part of what has enabled the devices to support both FDD and TDD in the same device and the same chipset without major headaches. It's by design. So, you know, there may have been some other dichotomies and splits, but I think that one is actually, from my perspective, is a huge success story.
So if we take that one as an example, how does carrier aggregation between FDD and TDD work? And will we anticipate that being a bigger issue going forward?
The standards support carrier aggregation between FDD and TDD.
Release 12.
Yeah.
Yeah.
Yeah, I'm not sure the timing of it,
Yeah.
but it's in the standards.
Okay, so you're
Release
saying
12.
basically we know about all these and we're going to deal with them in 5G as well.
Yeah, so you know, at 5G, again, we solved a lot of problems in LTE. All of the learnings and problems we solved will carry across into 5G. There are even, you know, new areas we're solving now with some of the work on Internet of Things and massive MIMO that you can consider preparatory work for what will be extensions and critical parameters.
So for
of
example,
5G.
shared spectrum?
Shared spectrum kind of capabilities, or you know, how you follow those rules, what you do with shared spectrum, what you do with unlicensed spectrum, are parts of what is in discussion in LTE now.
I think 5G is going to be, from the beginning, I think there is this well-accepted notion that we're going to have, from the beginning, think about a design that supports FDD, TDD, unlicensed, licensed spectrum, and in a way that is as seamless as possible. In particular, actually thinking about not as an afterthought, like as a, you know, we'll introduce something and then we'll make a fix that's later, 2 or 3 releases down the road, but actually making it as integral part of the initial design. It may not everything come out in the first release, but the important point is that the framework that we're going to lay out is going to enable all that seamless set of features to be brought in and support all these different combinations.
Yeah, I mean, if you kind of look at the progress on 3GPP standards, you know, we kind of started out, I'll just do 3G and LTE as examples, right? So 3G started out, it's 5 megahertz channel size, period. It's FDD, period. LTE says, okay, I got channel sizes ranging from a bit over a megahertz to 20. We did better, some, you know, discrete channel sizes that are options. In fact, we even added in 15 after the first standard was completed. And then we also put in FDD, TDD as part of it. So that's kind of like part of the design of LTE was to be more flexible than 3GPP and kind of take all the stuff that we learned, in 3G, and take the stuff we learned and carry it across to that. And I think that, you know, the pattern in 5G is not only a continuation, but an acceleration of that trend in terms of getting greater flexibility, ability to apply to a wider range and set of types of spectrum bands.
So isn't it, it's a case where carrier aggregation, you sort of generalize carrier aggregation, because right now carrier aggregation is within LTE, so TDD, so it's going to be even broader. And, but at the same time, could you also argue that because you're going to have so much spectrum, do you really need carrier aggregation, or is it the need is going to, because right now you have a need because there's so little spectrum that you need to do it?
Well, especially in the sub-6 gigahertz range, there's no magic spectrum being created, right? And I mean, we're pushing for and getting expansions, and there's new bands that can be worked on. So spectrum is still going to be a scarce asset, and I think the ability to aggregate across different bands, it has more value actually than just adding up smaller chunks of spectrum. That's one very clear value, but another significant value is frequency diversity. So if you can operate across multiple bands, and if I've got 3 devices in different parts, I'm the cell tower and there are 3 devices scattered out in this room, odds are really good that the efficiency, the spectral efficiency that I can get to for each of those 3 devices is slightly different, and sometimes significantly different, at different frequency bands.
Yeah.
So by figuring that out, I can actually get a better total allocation of the right frequency to the right device based on its conditions, and overall get more total capacity and speed than I could if I was just dealing with 1 band at a time and had each device on 1 band. So there are added benefits that come about, and 5G doesn't add it, or is planning to. It doesn't do anything yet, but the plans for 5G are to add in kind of a even more fundamental kind of concept behind carrier aggregation. So right now you kind of still operate each of the carriers in LTE as its own carrier. It carries its own framing and its own frequency band. You kind of add those together. Some of the 5G concepts are basically to say you can add them together kind of at the RF level, not necessarily at just the framing level. So you can get even more flexibility and have another set of tools to use to optimize the overall approach.
Mm-hmm. Yeah, and I think that the concept of frequency diversity, it's really a crucial one, because the reason why traditionally a mobile operator didn't want to use high bands is because of the limited coverage, and the limited coverage now becomes an asset because that allows you to reuse the spectrum more efficiently, yeah. Right? So in that case, for the same amount of spectrum, actually, it's much better.
Yeah. Yeah, and you need as you go to higher frequency bands, the carrier aggregation is going to be helpful with some of the reliability issues that we mentioned. Right. Also, think about transitions too. So very high frequency bands are good, but they probably you can get good outdoor coverage, you can get some decent indoor coverage, but it's unlikely that you'll be able to propagate outdoor to indoor. So those kind of things, in order to really provide a very good and robust user experience, going back to the notion of an anchor carrier, it's important. And there are multiple ways of doing it. The carrier aggregation way of combining lower frequency bands and high frequency bands, I think, is going to be proven to be the best approach.
Yeah. And maybe you can talk a little bit about the use cases in terms of where do you want to use the high frequencies, maybe only indoor, small cells, macro cells. What's the mix there? How do you see that happening?
Do you want to tackle it? Or?
Go ahead. Yeah.
So I think there'll be multiple scenarios. As I was saying, outdoor coverage is actually for many, looking at many propagation studies that we're doing and some other companies are doing, we're basically showing that you can get decent coverage, several hundreds of meters. So you can imagine a deployment where, you have some sort of a picocell outdoors providing good capacity and coverage. Also, you have the other case, which is indoor. There, it's depending on the frequency bands, a little bit more challenge to propagate through walls and things like that. So you could have in-room kind of coverage, which is pretty good. So that in that case, it would be a small, access point, small cell type of deployment. I think the important thing is to really look at it from a, you're adding more spectrum, access to more spectrum, because the demand for high capacity and high user experience and throughput is just going to continue to grow, and so you have to kind of aggregate more and more, frequencies and resources to provide the user experience that customers demand. So you're going to use it everywhere, as anywhere you can possibly make economical sense of that solution, then you're going to use it. You're not going to see it being used at high-powered cell towers, that's probably not the right setup, but everything else should be applicable.
Yeah. Okay, so let's look more at specific bands or types of bands. When we talk about high frequency, we think about 24 gigahertz and up. And the low end is like 6 gigahertz and below. What about in the middle? What's going on there? Is that an option for 5G?
Yeah, so I think clearly that's an option, and there's it's a range. I mean, typically that one can be more problematic in some cases just because of the multiple uses and the different uses in place and how you would do sharing and arrangements. But I think, you know, from what we're looking at, we want to look across the whole band and or the whole range of feasible frequencies and you know, see what makes the most sense. They're differing as you kind of get into individual bands and individual areas and individual countries and individual regions. You get, you know, interesting types of complexity. I mean, we're looking at it just within AT&T, right? We have a mobile network. We have a satellite network with DirecTV. We have point-to-point microwave links. And so, you know, part of what we're looking at as we go through the entire band is, okay, what can coexist? How can coexist? What makes sense? How does this stuff all work together? And there are going to be some, you know, interesting challenges. You know, you've got the DoD spectrum, the government use spectrum, a lot of different applications, a lot of different things happening in different places, and that's part of the reason that the spectrum set of issues isn't like, oh yeah, easy, check. Yeah, there are challenges, and we need to work through those.
Yeah, absolutely. Now, what about the 3.5 band? There's a lot of interest, and is it going to be used LTE, 5G? Wi-Fi-like?
That's a good question. I think the initial thought would be some form of LTE for 3.5, but the final details of the band are still, you know, TBD. And I think, you know, it's a good question, and depending on the timing of the actual deployment, whether, you know, it would make sense to use 5G at that point in time or start with LTE. I think it's a good question. I think we'll probably see LTE deployed in 3.5, but, and I'm referring to the 3.5 in US scenario, right?
Yeah,
which is not in Japan and other parts because there is more clear. But, you know, but depends on how it goes. It could be delayed and maybe an opportunity for 5G. Same for, I would say, same applies to 600 megahertz as well, which, you know, depending on the time of that, it could be very well that by the time it's all clear and ready to go, it's, you know, 5G is available, so who knows.
We have a question. Actually, before we get there, another question is unlicensed spectrum. So with 5G, you are going to be able to access more spectrum. Does it mean that mobile operators will be less inclined to use unlicensed spectrum and Wi-Fi for their networks? I guess, Hank, that's for you.
So I guess the way I look at it is that, you know, if you look at the unlicensed spectrum range, there's LTE, LAA kind of range that uses the LTE waveform that's being worked on as a part of R13. There's also LWA, you know, using basically the Wi-Fi waveform, but then tying that back into the LTE network. I think both of those are good uses. They're, you know, have their areas where one may be stronger than the other, but both good areas and use cases. But you know, just kind of like we talked about LTE kind of pioneering some of the technologies that are likely to carry forward into 5G, I wouldn't see any reason that unlicensed spectrum should also carry forward into 5G.
As well. Okay. We have a question.
Yeah, I have a question. I think we talked about three things: carrier aggregation, sharing of the spectrum, and the frequency diversity, right? So we understand that carrier aggregation not possible between all the combination of the bands, right? And certain time, some bands are not fully utilized from that operator that owns it. So with respect to the sharing of the spectrum, do you see, you know, from the chipset perspective, right? not supporting carrier aggregation, but how do we support the sharing of the spectrum between the different bands? And what are the challenges that you can think of? It may not be carrier aggregation, but just sharing of the spectrum, kind of loaning out part of the spectrum to be used by the other carrier. Do you see that coming?
I'm not quite sure I understand what you're asking about.
So basically, all I'm asking is, between the different bands, it may be the bands within the 700 megahertz, right? All the bands may not be fully utilized by the operator who owns those bands, right? Do you see, and carrier aggregation is not, it's not in place, right? Do you see, based on the usage type, the less used band could be shared or loaned part of the spectrum to the other band? Do you see that happening, and what are the challenges from the chipset perspective?
There's a lot of different definitions of sharing and how sharing can work, and coordination and sharing and some of those aspects, right? So if you look at Wi-Fi and then the LTE, LAA, they do sharing by kind of cooperating and using a common listen before talk protocol that effectively sets the spectrum across different areas. There's a sharing being proposed for the 3.5 gig band in the US. Uses a SAS, basically an entity that kind of says when you can and when you can't, and kind of helps assign and coordinate the spectrum. And one of the things you're sharing with is government use of the spectrum that takes priority, and if the government is using it, you don't use it, and that can change dynamically in real time. So there's a lot of different potential models of unlicensed. There's fully licensed, and I think if you've got fully licensed spectrum, you can get the maximum possible efficiency out of it because you know exactly where all the cell sites are, what they're doing, what power levels they have. You can maximize handoff, you can cancel interference. You can do a ton of stuff in dedicated licensed spectrum to absolutely maximize spectral efficiency and to absolutely provide ultra-high reliability services. As you go into the differing degrees of sharing and the different types of sharing, you get different parameters, different behaviors, and things are going to act differently. So I would have to guess that we may see continued developments in sharing and different types and coordination of sharing. But even in the FCC NPRM basically said, the kind of sharing that we're developing for 3.5 gigahertz, why don't we look and see, can we apply that to one of the millimeter wave bands? So, I think sharing is going to be around. It's going to be different for different bands. It's going to have different parameters and different technologies. The more different approaches, the more complex and difficult things are going to get, which decreases efficiency and increases the technical challenges. But it's kind of a fact of spectrum use. If we're trying to get maximum capability out of spectrum, the approaches that are being worked now are ones that are being worked through industry consensus and approach. I think that's the model we've got to do going forward. There's a lot of very cooperative work in trying to define how these bands work.
And from the chipset perspective, do you see that's coming along, and what are the challenges do we see from chipset perspective, whereas the sharing of the spectrum is concerned? Maybe it's a question for Eduardo.
So I'm looking at it, I don't see a bigger challenge from a sharing perspective, if I understand your question correctly. So the moment you define technologies that are going to either coexist in different bands, like Hank mentioned, or going to aggregate. So essentially, it's a carrier aggregation solution, which we support already, multiple combinations of carrier aggregation. So it is unclear that the challenge, the fact that it's shared, depending on what you mean by shared. If you mean, different additional combinations of carrier aggregation because of the sharing aspect, then then that's something that needs to be analyzed. I don't know exactly what you mean by that, but I don't expect.
I can take it offline.
Yeah, we can take that offline.
Yeah, so, sorry, another question here?
Quick follow-up on the question of spectrum sharing. Well, I think we really have to be careful. Are we talking about lower bands or upper bands? For example, I mean, we're looking about noise limited versus power limited. The higher up you go into spectrum, you're looking at narrow beams. You really can do, you can use the exact same block of spectrum between multiple vendors and you have absolutely no interference, just because the beam tend to be very, very small, especially for fixed use. But for mobile, that's a different story. So I think when we're talking about spectrum sharing, we have to be very specific. Are we talking about lower bands, upper bands, middle bands, because of how the physics work? What do you think, Hank?
So I think what you stated is a specific example of the fact that you can't say spectrum sharing and really mean anything. I mean, right, frankly, because spectrum sharing is a very, very broad concept, and it isn't the case that one solution is spectrum sharing, right? You've got to look at specifics of each area, the frequency band, how it's used, who's sharing it, what the applications are, what the propagation techniques. It all has to come into play, and that's kind of why we're kind of still at in some of the areas, we're still at the experimental phase in it, right? Nobody's implemented the 3.5 SAS spectrum sharing to see exactly how it works yet. We don't even have everything kind of finalized and worked out. So it's going to take time to develop, and I think the approaches of one step at a time and learn and then move on is a good approach.
Question over here?
I would think, if I can explain it clearly, but how high in spectrum do you see LTE going? I mean, obviously, 5G is going up, up, and up, and LTE has been creeping up. But is there, because of 5G, a place where LTE kind of stops, or is it going to be blurry and complicated like it usually is? Or can you say, 6 gigahertz, that's where we draw the line with LTE, and thou shalt not go above it because it just doesn't make any sense? Do you get the question? And
yeah. So I think, it's good. This is a good question. I think you see, LTE. So fundamentally, if you are trying to support frequency bands, very high frequency bands, you have to make changes to the waveform to accommodate for the new frequency band, for the very high frequency bands. So clearly, the LTE design as is would not apply, but for frequencies maybe up to 6 gigahertz, it's still applicable. And so that, for instance, we see all the work in LTE U and LAA in 5 gigahertz. The other aspect is, from a practical perspective, I think as 3GPP starts working on a new air interface with 5G air interface, so the need to go back to LTE and try to change it to accommodate for these higher frequency bands is going to be less, right? So I don't see it from a practical perspective happening. What is the right number, ceiling? We have to do some calculation. I don't know. Maybe 6. Also because, around 6 gigahertz, we're not going to find any bands anyway. So after that, there is a big jump. So probably it's not going to work.
So can you tell us a little bit about what kind of air interface and modulation we could think of for the high bands? How different it's going to be from LTE? Or is it still open?
Well, there's some, yeah, it is open because the studies haven't started yet. It has started yet, so I think we need to wait for that. But I think when a lot of people talk about, is this going to be a dual modulation scheme, and different companies have come up with different names for their proposals, and when you look at it, it's essentially all within the family of what we call OFDM type of modulation, because it's all a matter of kind of dealing with FFTs and IFFTs, and and dealing with timing, frequency, resource partitioning. You may do different type of filtering, different type of windowing in time, and so forth, and then you call it a different name. And there are some benefits for doing some changes. So I think what we'll see is a variation of that team, and with different parameters that will be utilized for lower frequency bands, and different set of parameters utilized for high frequency bands.
Any more questions from the audience? Okay, let me ask you this. If you were to pick and choose the best candidate band in terms of really showing the best case for 5G and being realistic, what would be your choice?
I don't know. I mean, at this stage, it's kind of hard to tell. I think that one of the interesting candidates, and in part because it's already being discussed, is 3.5 gig band. Right, that's being discussed in Asia as a licensed band, and we've got the potential for an unlicensed, let's call it unlicensed, GAA, LAA, the kind of interesting arrangements in the access techniques in the U.S. So that's one of the interesting possibilities, but it's I think it's kind of early to tell right now. It depends on the timing and the way things get defined. 5G will be defined pretty flexibly to work across a wide range of bands. So I think it's going to be less, is there a band that matches the technology, and more that, what bands are available at the right times for when you need them.
Yeah. I think in the sub-6 gigahertz, 3.5 could be a candidate. There are a lot of discussions, in particular outside the US, around 4 gigahertz, 4.2 in particular. This could also be used here in the US. There's still some discussions. So I think that could be a good band, because outside the US in particular, there's availability of hundreds of megahertz at 4 gigahertz. So be able to fully explore these notions of very wide band channels, and be able to do massive MIMO, and the frequency band is really appropriate for that. Then when we go above 6 gigahertz, that's a little trickier, because we need to wait for WRC, and different countries will have different choices of bands. It's unclear which ones are going to be the first ones to be adopted.
Yeah, in terms of spectral efficiency, how much of a benefit should we expect compared to LTEs? Because some of the benefits come from the fact that you have more spectrum in the higher frequencies. But if we forget about that and we look at the bits per second per hertz, is that going to be much better, or compared to LTE? And if so, where is the improvement coming from?
Yeah, I think some of the key components. So from a pure link perspective, if you look at modulation, coding, and all of that, so I think it's well established the fact that we're really getting close to Shannon capacity. So it's very unlikely that we'll come back and say, oh, we're gonna double the performance based on link performance. But from a system perspective, when you take into account the various nodes and the various devices and how you deal with interference, interference coordination, things like the rule, interference cancellation schemes done in a different way. Massive MIMO is a technology that can provide significant gains. I think if you look at even the frequency I mentioned, 4 gigahertz, for instance, we are seeing potential system level gains of a factor of 3 to 4, depending on some of the assumptions. So it's very relevant, but it's going to be like a system level gain, not modulation coding scheme.
And then, I think the other area mentioned is that another kind of area in the system level gain is if you look at massive Internet of Things kind of traffic, right? LTE, if you kind of follow the traditional kind of, before narrowband LTE capabilities, if you want to send 100 bytes, you have to signal, set up the connection, get everything synchronized, send it, tear down the connection, and it's, LTE is very spectrally efficient, as you said, Shannon limit and using interference cancellation and other techniques, if you're sending a lot of data, but not so much if you want to send 100 bytes. And I think that's the other thing that 5G will bring, is that the connectionless layer, the massive Internet of Things kind of layer at 5G should be improving the efficiency for that type of device, another area of improvement.
So it's an improvement instead of just going the high end of extreme capacity, extremely low latency, but there is also the need to basically support a high number of devices, which is something that we often don't think about it, because we say, well, we know how to do that. But when you have a massive number of devices, that's also another challenge. And you think that 5G will be able to address that better?
Yeah, I mean, it's one of the kind of use case areas that I'm really excited about, because I think it's, it can generate a wide range of potential new applications and uses that we haven't kind of thought about yet even. So I think that what both narrowband LTE will bring into that and what 5G will continue and extend in that area are both going to be really kind of exciting to watch as we develop.
Mm-hmm. Now, what about other sort of solutions like full duplex that are sort of trying to, again, to go past Shannon kind of thing? What do you think? There is an opportunity there, or is it?
It's definitely an interesting technology. In particular, when applied to network nodes like relays and small cells. The potential for using the given bands, for simultaneously transmitting and receiving is very attractive. You get, if everything goes well, you get a factor of 2 improvement. But there are some challenges when you look at other more general applicability and from a device perspective, like if you're trying to provide that kind of traditional use case of network node to devices. So but it's definitely an interesting technology that many companies are working on right now.
Yeah, but when you have solutions like that, it sounds very attractive. But then the standardization process can be more difficult in the sense that you're introducing something new. And how do you balance the need, the attractiveness of a new solution versus the need to standardize it? And I guess it's nothing new, but how do you think it's going to play out in 5G?
Which
if you go like a full duplex, you need to have it standardized, and so it's not just if you use it on a point-to-point type of situation, you can do whatever. But in order to extend it, you need to have all the consensus, and how difficult it is to get to that point. How long is it going to take, you think? You see what I mean?
Yeah. So I think the way I look at it is that to standardize a technology, you have to have a pretty good concept around how it works and how effective it is and how you make it work in a standard way, right? And so, full duplex I don't think is quite there yet. I agree, it's got a very interesting technology. We've been doing some experiments with it, and it's got a lot of kind of interesting capabilities. But I don't know that anybody's kind of brought in and say we should standardize full duplex yet. I don't think it's quite ready from that standpoint. But that said, there are some things that you can add in, take the narrowband LTE capability. There are some things that you kind of add in after even the basic standard is in place without, totally upsetting everything and kind of messing up the existing standard to make it compatible as it goes forward. So I think that LTE has definitely proven that it has flexibility and options to do that. And the thing I like most about 5G is that it is being designed from scratch to be far more flexible than LTE. And so it's, I think as full duplex comes in or other types of technologies, the ability to incorporate it within the 5G schema is it's going to be highly probable, I think, that we can do that in an effective way.
Yeah, our time is pretty much up, but if you have any closing thoughts that you want to share with the audience.
Yeah, I would say, 5G is definitely a very exciting topic. It's growing in interest. The industry has been working together on trying to define what 5G is going to look like, and I see a lot of common views at this point compared to last year when I was here also talking about 5G. So I think this is very exciting, and the work in 3GPP is going to start soon. And yeah, so I think that we should kind of put a lot of effort in that design, but at the same time, realize that LTE has a good path forward. It has a lot of features being developed in Release 13, and we continue to introduce new features in Release 14, 15 as well. So I think this is an exciting time.
Yeah, I agree. I think, just to kind of emphasize on the point of the LTE capabilities, there's a lot of stuff that you get an idea that's, can say, let's make 5G do kind of this connectionless capability. Okay, well, we can put that in LTE as well, get an earlier version of it, and in the meantime, learn a lot about it, so when we create the 5G standard, we're actually going to have a better standard than we would have if we didn't move it back into LTE. So I think that the interplay of the technology ideas, both going into 5G in a longer-term version and fitting into 4G LTE is synergistic. It's really kind of cool to see the entire world standards activity focused on 4G LTE and 5G instead of being split across different brands or types of technologies. That kind of key focus and synergy of the entire community in those areas is really exciting. It hasn't happened for a long time.
Yeah, well, thank you so much for your insight and you for participating.
Thank you.